Hello viewers, welcome back to my channel. Hope you are doing great. If you haven't subscribed to my channel yet, please go ahead and subscribe. I have created several playlists to cover various categories of problems such as dynamic programming, breadth first search, depth first search, sorting, trees, linked lists, strings, arrays, and so on. So don't forget to check them out. I have also uploaded the code for this particular problem to GitHub repository. You can get the link from description below this video. Let's jump into today's problem. Single element in a sorted array. You are given a sorted array consisting of only integers where every element appears exactly twice except for one element which appears exactly once. Find this single element that appears only once. So basically we are given with a sorted array where every element except one appears exactly two times and that one element appears exactly one time. So now we need to find out what is that one element which appears one time, right? So if you go look at the example, right, 1 so 1 appeared two times, 2 appeared only once, 3 2 times, 4 2 times, and 8 also 2 times. So obviously when you look at it, you need to recognize as okay, 2 is the one which did not appear two times but it appeared only one time. So that's the answer, right? So in the example 2, right, so 3 2 times, 7 2 times, 10 only one time, and 11 appeared two times. So here again look at it, it's 10 is missing, right? 10 is missing there. So there are several ways to solve this problem, right? So let's try to look at some of the ways to solve this problem, and we try to solve in the most optimal way possible, right? So there is a node that is given here. So your solution should run order of log n time and order of 1 space. That means order of 1 is a constant space, basically order of logarithmic time, and space is constant, right? So let's try to work out a solution by examining several solutions. Okay, so one thing that could come into your mind is, okay, let me keep track of the count of each element that occurred, right, and how many times it occurred. We already know except one, every other element occurs two times, right? So we can keep a map and fill the map by going through the array. Once you fill the map, go through the map again and try finding that element which occurred only once. So it's something like this, right? So you prepare a map. So 1 occurred, so this is for the example 1. So 1 occurred two times, and 2 occurred one time, and 3 occurred two times, right? 4 occurred two times, sorry, and also 8 occurred two times. So now that we have this map, right, so we go through this map and try to find out which occurred only once. So that is 2. So this we return this basically. So this is one way. But what is the time complexity for this algorithm? So we are going through the entire arrays. Let's say the length of the array is n, right? So time is order of n, right? Order of n, and space is since we know every element occurred in two times except one, right? So that means the space required will be order of n by 2, right? N by 2. So this will be a time complexity order of n, and space complexity is also order of n because we often tend to remove the constants from the big O notation, right? So the time complexity is order of n, space complexity is also order of n. But what we are looking for is the final solution is order of log n and one space, right? So let's go ahead and examine more, right? So this is one approach. So the second approach that we could use is you actually don't need this space. Let's try to trim this space to 1, right? So you go through the entire array by keeping the counter, and since the array is sorted, we know that, and you increment the counter. When the counter reaches to 2, you reset it. That means you will see a next element, right? Once it reaches 2, you should see a next element as different element. But at any place, if you see a different number before reaching the counter to 2, right, that is the number which occurred one time, right? So likewise, you can keep track of the counter, and whenever you see a different number when the count is at 1, that number, right, that number or the previous number will be the answer for you. So what will be the time complexity for that? Time will be still order of n, right, and space will be order of 1, because we are just using counter, right? So now the space requirement is met with the node that is given here, right? Now we'll have to try to work out the time requirement, right? So there is one more way, one more easier and better way to solve this. So let's use the XOR operator. So there is a bitwise XOR operator that we can use to come up with some kind of solution, right? So this is the XOR table. So let's say x and y are two operands. When both are 0, XOR value is also 0. When 0, x is 0, y is 1, XOR is 1. When x is 1, y is 0, XOR is 1. When x and y both are 1, XOR is 0. So essentially, when x and y both are same, right, the XOR of them will be 0, right? When both are same, 0 0, then it is 0, or 1 1, it is 0. But if they are different, then only they are 1. Okay, that is the XOR truth table we call. So now what we can do is, what this is giving you, if the elements are same, that means they are cancelling out, right? For example, this 3 and 3. So if you do 3 and 3 XOR, it will be 0. 4 and 4 XOR, it will be 0. 8 and 8 XOR, it will be 0. 1 and 1 XOR, it will be 0. So 0 XOR all others is 0 anyway, right? And 0 XOR 2 will be 2. So that is what the approach we are going to do for this, right? So when you do XOR for the same numbers, the result will be 0, assuming that the same numbers are repeated even number of times, right? Because we already know even number of times, because it is only appeared twice. So same number appearing 2 times will cancel out each other, and the XOR will be 0. So whatever the element that will be left will be the one which occurred just once. So that's one way. So if you look, right, so we are still going through the entire array, right? So the time complexity is still order of n, but space is still order of 1, because we just use single variable to keep track of the XOR across the element. So we essentially do the cumulative XOR, you could say, right? But here still the time complexity is order of n and space complexity is order of 1. So whatever we do in these format, right, we are still going through the entire array and trying to come up with the solution, right? So when you see order of log n, right, so there is a algorithm which need to come into your mind. Basically, log n will come in places where you are reducing the search space into half for every comparison. So what you can think in that way is, there is a search called binary search, right? So binary search is, at every step you will be reducing the search space into half. So if you have 10 elements to start with, so after the first comparison it will be 5 elements, after that it will be 2 elements, after that it will be 1 element. So finally you get the answer. So even if it is 10 elements space, 10 elements are there, within 3 comparisons you are out with an answer, right? So likewise, log n is, always think about the binary search criteria, right? So we will be doing a modified binary search for this. So we already know that for binary search we need array to be sorted. Yes, the given array in this problem is also a sorted array, right? So that condition is met. So then we will have to do a slight change in the binary search. So one thing that we can know is, all elements appear twice except one, right? So that means the length of the array will be always odd, right? Because n minus 1 elements appear even number of times, that is 2 times, and 1 element appears 1 time. So the total number of elements in the array will be always odd, right? So that we figured out now. So now the element which occurs only one time could be on the left side or right side of the mid. So basically the binary search works this way, right? First we calculate the midpoint and try to compare the target with the midpoint. If the target is greater than the midpoint, we will search in the right half. If the target is less than the midpoint, we try to search further in the left half, right? So that's how we are doing. So in the same way, we have to come up with a algorithm here, right? So we will do a modified binary search, right? So when the midpoint is odd, what to do, and when the midpoint is even, what to do. So those are the two things that we will be using. So those are the 2 points that we need to fill, so that we will complete the algorithm, right? So if the midpoint is odd, right, so then we will have to check. So for example, let's take this, right, the first example 1, right? So the length is basically the start is 0 and end is 8, right, because there are 9 elements, right? Yes. And what will be the mid? Obviously mid is 8 plus 0 by 2, mid is equal to 4. So that means we will be comparing the 4, 0, 1, 2, 3, 4, 4 is this one, right? So now we will have to compare. If the mid element is same as mid plus 1 element, right? If the mid element is same as mid plus 1 element, that means, right, what does that mean? The number of elements occurred so far onto the left side are in the correct order. That means every element occurred 2 times, right? So if the mid element, let me write that down actually, nums of mid is equal to nums of mid plus 1, right? So this is what we are trying to compare. If the nums of mid is equal to nums of mid plus 1, so mid, what we said, is 4, right? 0, 1, 2, 3, 4, right? So if this is equal to this, that means onto the left side all the numbers are in the way that we want. That means they appeared 2 times, right? So if that is the case, our element which appeared in the right side should be on the right side, right? So that is the conclusion. What we are going to do is, our search space will start is equal to mid plus 1, right? So that's one condition. But if it is even, so some point in time the mid could be even also, right? So in the mid, if it is even, what we are going to do is just a slight change here. We are going to compare it with mid minus 1. So that is the change that we are going to have, okay? In both cases, what we are going to do is start is equal to mid plus 1, okay? So that's what it is. But if any of these 2 conditions doesn't meet, right, if nums of mid is equal to nums of mid plus 1 or nums of mid is equal to nums of mid minus 1, if these 2 conditions doesn't meet, right, then what we are going to do is, obviously we are going to do it on the left side. So in that case, what we do is left side, right? So left side means we would do end is equal to mid, right? So we have reduced the search space into half at every step basically. So if it is odd or even, assuming these conditions met, right, nums of mid is equal to nums of mid plus 1 and nums of mid is equal to mid minus 1 in case of even. In both cases we do start is equal to mid plus 1, but otherwise, right, if these numbers match or don't match, right, mid and mid minus 1 or mid plus 1, what we are going to do is end at mid. So likewise we continue, right? So at every step we are trying to reduce the search space into exactly half, right? So since we are trying to reduce the search space into half, this will certainly follow the binary search mechanism. whereas we get the time complexity as order of log n. So let's go ahead and jump into the code, right? So as we said, we initialized the start and end elements, right? So 0 and num minus 1, so num dot length minus 1. So while start is less than end, we are going to go through this loop. Basically, we are trying to reduce the search space, right? So we take the mid is equal to start plus end minus start by 2, right? And if mid percent 2 is equal to 0, this is nothing but even, right? If it is even, right? And this is nothing but odd. So likewise we are going to see and increment the start is equal to mid plus 1, otherwise end is equal to mid. So that's the code that we are going to use in order to solve this problem. So finally, whatever the start element that you stop, right? So that will be the answer. So the time complexity for this will be order of log n, and space complexity is order of 1, because we are just using start, end and mid integer variables, right? So everything else should be fall in place. So this algorithm satisfies our requirement of order of log n time and order of 1 space. So I have XOR based code also right here. This is very simple. Basically, this is order of n and order of 1. So you put the answer, you initialize the answer with the first element in the array, and then go through the entire array from 1 to num dot length and try applying the XOR. So whatever the element that is left in the answer will be returned. So this is for the XOR case, the third case, right? So this one, yeah, for this case, basically we have the XOR table and try to come up with that, right? So it will be order of n and order of 1. So obviously this is the worst, and this is the next, and this is the next, and the most optimal that we want is order of log n is this one, right? So that is what we have coded for, right? So finally we got a order of log n time and order of 1 space algorithm. So if you have any questions, please post them in the comment section below this video. I have posted the code to GitHub repository. You can find the link in the description below this video. If you haven't subscribed to my channel, please go ahead and subscribe and also share among your friends. Please click on the bell icon so that you will be notified with all my future videos. Thank you for watching. I'll be back with another problem very soon. Till then, stay safe and goodbye.